Hey guys, welcome back. Second part of Learning Guide 14.2. We're just going to pick it up right away with the second part of Learning Guide 14.2 because this is it's an involved part of the unit. It's a very involved topic. It's one that we use often in AP Chemistry when making reference to equilibrium. So in Learning Guide 14.2, we're starting on objective number 7. To illustrate the ICE method, then we're going to summarize it, and then I'm going to show you a couple of practice problems using it, and I'm going to try to do it a different way with the smartboard. Hopefully it works. And then I will definitely add some extra resources for you as it relates to equilibrium in K versus Q before we move on to Learning Guide 14.3. All right, so we're on page 635 of the textbook. And to illustrate the ICE method, they make reference to an example involving an organic substance referred to as stilbene. It's an organic solvent. You can see the formula for it at the top of the screen, C2H2Cl2. Because of the double bond in between the two carbon atoms, we might as well start using some of the terminology that we've been using since the beginning of the year. We can make reference to hybridization here. Because the carbon atoms in the center both have a total of 3 other atoms bonded to them, we can make reference to them being sp2. Because of the double bond in between the 2 carbon atoms, we can make reference to the pi bond and the sigma bond. The difference between the 2 molecules on the left and the right is the orientation of the chlorine atoms with respect to one another on a flat plane. You can see that a cis molecule has 2 chlorine atoms that are on the same plane as one another, as illustrated on the left here. So the 2 chlorine atoms are apart from one another on the same side. Whereas in a trans molecule, they are opposites of one another. You can see that the 2 chlorine atoms are diagonal from one another. So this is another type of isomerism that you're going to get into more in depth when you get into your second year of college chemistry. If you remember, isomers are compounds that have the same formula but different structures. It's a different type of isomerism, which, like I said, you get into more in organic chemistry. So the problem that they use in the textbook on page 635 involves this cis-trans form of stilbene. So I went a little too far here. All right. So the example that they use is a cis-trans form in which the equilibrium constant is 24.0. Again, keeping in mind that equilibrium constants tell us that when the equilibrium constant is greater than 1, that means at equilibrium there's going to be more product than reactant. So if we were to write the equilibrium expression, it would be the transform, the product, because of the way that we wrote it. And remember, the way that we wrote it with the trans on the product side means that the products over reactants quotient is 24.0. Now, if we were to flip the cis and the trans sides here and put the cis on top and the trans on the bottom, the Kc would be equal to 1 over 24 would be the reciprocal. So if we were to start initially with just a 0.850 molar concentration of cis in a closed system and no trans at the beginning, the question is, what would the equilibrium concentrations be at the end? And so ICE in the ICE method refers to initial change equilibrium, ICE. The change line here is always going to be equal to variables equivalent to the stoichiometric coefficients. So here, the cis can only go down and the trans can only go up. And the reason for that is because in order to reach equilibrium, you're starting with just cis. And according to the equilibrium expression, at some point there's going to be an amount of cis and trans equal to a quotient of 24.0. So the cis can only go down because that's your starting amount, and the trans can only go up because you're starting with none of it. It can't go down from 0. The equilibrium line, the last line, is always your starting amounts relative to the change. So here the starting amount of 0.85 goes down x to 0.850 minus x. And again, the reason it's x is because there's only 1 mole of it that can go down. And the reason that this is equal to x here is because only 1 mole of it can go up. So these are your equilibrium amounts relative to your starting amounts, 0.850 minus x and x. Now, if we take these equilibrium amounts and we plug them in over here to the equilibrium expression, we get 24, the equilibrium constant, equals x, the trans amount, over the 0.850 minus x. And at this point, we would solve for x and then plug them back into the equilibrium expressions here at the bottom of the ICE box. So 24 equals 0.850 minus x times x. Distribute the x, solve for x. X equals 0.816. Now that x value is rational when you think of it relative to the starting amount. The x value can never be more than the initial amount of 0.850. So the 0.816 seems rational. Now what we're going to do is we're going to plug in this value of x into our equilibrium amounts here. So the 0.850 minus 0.816, so that's how much it went down over time. You get an equilibrium amount of 0.034. And the trans just went up the equal amount that this went down because it's a 1-to-1 ratio. So for every mole of cis that was decomposed, you got a mole of trans produced. So because this went down 0.816, this went up 0.816 to a final amount of 0.816. So that's how we would use the ICE method. Okay, before we go on to the next one, let's just summarize what we saw illustrated there in that example problem of the cis-trans still being an example. So when calculating equilibrium expressions, express the equilibrium concentrations of all the species in terms of the initial concentrations, which in that example was the 0.850 and the 0. A single unknown x relative to the stoichiometric coefficients, and those are going to be the changes. The one that has a starting amount goes down. The one that has an amount of 0 initially is always going to go up. Write the equilibrium constant, that's Kc equals or Kp equals in terms of products over reactants. Knowing the values of all the constants, solve for x. Having solved for x, calculate equilibrium species. And I'm not going to go into this one. All right, here's a second example, which is in our textbooks on page 635 and 636. So it's a problem involving hydrogen and iodine producing hydrogen iodide with an equilibrium value of 54.3. You can see that you start with H2 and I2 and no hydrogen iodide initially. So if you were to put hydrogen and iodide into a closed container and allow them to reach equilibrium, the equilibrium constant at some point is going to be 54.3. Now again, because the equilibrium constant is greater than 1, that means that once equilibrium is achieved, HI is going to be greater than H2 and I2. So if at the end that doesn't seem to work out, you know you made a mistake because this is greater than 1. So again, start by writing the equilibrium expression. Products over reactants raised to their stoichiometric coefficients. The reason we use brackets here is because this is in terms of molarity. Now, unlike the last problem, where it was just minus x and plus x because of the ratio of 1 to 1, here, because the ratio is 1 to 1 to 2, for every mole that H2 and I2 go down, you're going to end up with 2 moles of HI. So it's 2x here. And again, similar to what we did here on the equilibrium line, .50 minus x, .50 minus x, and 2x, because 0 plus 2x equals 2x. If we take these equilibrium lines here, the E and ICE, and we plug them in over here to the equilibrium expression, we get 54.3, what Kc is equal to, equals 2x squared over 0.50 minus x times 0.50 minus x. Now we can simplify that. I don't care about that right now. To 2x squared over 0.50 minus x squared. So to get rid of these squared values over on the right side, we can take the square root of both sides. Taking the square root of both sides, we get the square root of 54.3 equals 2x times 2x over 0.500 minus x. Solving for x, we get 0.393. Now, like we did back here, we can plug in the value that we found for x into here and here to solve for our equilibrium amounts. So we would plug the 0.393 in here, the 0.393 in here, and 2 times 0.393 here, which again makes sense logically because two things: the value of x is less than our initial amount, and when we get done, we're going to have a greater concentration of product than we are reactants, which is consistent with a K that's greater than 1. So plug them in there then. Now, here is another example that I want to illustrate that you can, I want you to take two things away from this. So here's an example where, again, it's the same reaction as the previous one, except our starting amounts are going to be different. Here, I'm giving you starting amounts of all three things. What makes this type of problem more difficult and more involved is the fact that you have to first determine which direction does equilibrium have to go to first. Do you have to, is this reaction currently one where there's more product than reactant at equilibrium, or is it one where there's more reactant than product at equilibrium? So essentially, to start, we got to go back to these problems back here when we were looking at Q versus K. So in a problem like this, the first thing you would have to do is solve Q. So the products, 0.0224 squared over the reactants, 0.00623 times 0.00414. When you solve for Q, you get 19.5. So thinking back to the first half of this lesson, what does that mean? Well, Q is less than K. So what that tells you is that hasn't gotten to equilibrium yet. So that means that the products still have to increase and the reactants still have to decrease. So that means these are going to be minuses and these are going to be pluses. So minus x, and plus 2x. That's the first half of this problem that makes it more difficult. Now, if we continue, the second half of this that makes it more difficult is solve for E, plug it into our K. We get this equals 54.3. Now, thinking back to Algebra 2 trig, what's the only way we can solve X here? Only way you can solve X here is if you use quadratic equation. Nobody wants to use a quadratic equation. I'm sure most of you remember Miss Spa singing the quadratic equation song in class. You don't have to use it. Rest assured that on the AP exam, every problem involving equilibrium problems can be solved without the use of the quadratic equation, like the first two examples. You will never have to use the quadratic equation. All right, so, oops, my bad. What have some previous problems on the AP exam look like? So I'm going to show you two examples of problems that have appeared on the AP exam in recent years so that you can get an idea for when is the ICE method of determining equilibrium amounts been used. So they gave students a problem where there was an equilibrium system between normal butane, that's C4H10, and isobutane, which is an isomer of butane. They will reach equilibrium with a constant of 2.5 at 25 degrees Celsius. So that means that it's going to be really close to an equilibrium value of 1. So that means these two at equilibrium are relatively equal to one another. So if you had a 1 liter container and you had 0.010 moles of N-butane, and you had to figure out what would be the pressure at the end, for example. Well, remember, in equilibrium expressions, it's got to be in molarity. So the first thing you have to do is divide the 0.010 by 1 liter, which is just 0.010 molar. So if you start with that, initially you have 0 isobutane. So we can now set up our E's or our C's. So it's a 1-to-1 ratio here. So it's iso over N-butane, products over reactants. That has to go up some amount. N-butane has to go down some amount. So you're going to get 0.010 minus X and X. Plug those into the equilibrium expressions. You get X equals 0.0071. So that would be the molarity of isobutane, and then the molarity of N-butane would be 0.010 minus 0.0071. So if you plug those in there, and then if we solve for PV equals nRT, the volume is the 1 liter container. The N is the 0.010 moles. R equals 0.0821. And the 298 came from the fact that it was at 25 degrees Celsius. Solving for P, the pressure would be 0.24 atms. You could solve for either the equilibrium concentrations here or using PV equals nRT. We could solve for the pressure initially. Here's another last example. This was on an AP exam a couple years ago where they gave students a solid U3O8 reacting with chlorine gas to produce 3 UO2, Cl2, and O2 gas. So they gave students an equilibrium expression. Now notice in this equilibrium expression, the U3O8 is nowhere to be found here because it's a solid. Remember, solids are never included in equilibrium expressions. So at equilibrium, they tell the students that the chlorine gas had a pressure of 1.007 atms, and the pressure of UO2CO2 was 9.734 times 10 to the negative fourth atms. They asked students two things: what was the Kp and what was the pressure of O2? So first, how would you figure out the pressure of O2? Well, if you take a look at the balanced equation, we see that the UO2CO2 and the O2 always form in a 3-to-1 ratio. So if we know the pressure at equilibrium of UO2CO2, we know that that's going to be 1/3 the pressure for oxygen. So that 3-to-1 ratio tells us that the pressure of oxygen is going to be 3.24 times 10 to the negative fourth atms, based on molar ratios. Now, if we know the Kp expression, we can plug in these partial pressures into the Kp. And again, watch your use of brackets, watch your use of parentheses when you're solving with these numbers that are written in scientific notation, and you have to raise them to a specific power. Kp is found to be 2.931 times 10 to the negative 13th, which again, think about the rationality of this value. It's much less than 1, which is consistent with the fact that at equilibrium, you have a much greater concentration of, or a much greater pressure, partial pressure, of reactant than you do products. All right. Hopefully this helps. Watch it a time or two. We will begin the next lesson on Learning Guide 14.3, which is Le Chatelier. See you guys.